So we're going to go ahead and get started. We have 2 sections left in our unit on limits. So just a quick reminder, this course we're going to go through 4 units. Limits, derivatives, which are my favorite, applications of derivatives, probably the hardest, and then integrals, which is another favorite. So there are 4 units. So we're coming very close to the end of the first unit on limits. Our test is next week. Today, probably teach till about 10:45. I'm going to get through a good amount of material today, and then let you guys get back into your groups to get started with our second lab. I will give an extensive, whatever we don't get through in 2.6 today, I'll finish up on Thursday. And don't worry, I give a nice extensive test review, so you'll know exactly what's going to be on the test. And then you have this weekend to catch up and complete all your math labs and to study. All right, so everybody knows where we're at. So last class in 2.4, we discussed infinite limits. And what we found is when you have infinite limits, meaning the limit at a certain value of a goes up to infinity, what we tend to have are vertical asymptotes. And we found that was our vertical asymptotes. But now we're going to look at limits at infinity. And what that basically means is what happens when I take my x value and take it off into infinity. Or I take my x value, because infinity goes in both directions, correct? We have positive infinity, or we have negative infinity. So think about this for a minute. What we're essentially doing here is saying, hey, what's happening to my function as I go off into infinity on the x, or as I go off into negative infinity? What we're looking at is the end behavior of our function. Okay? So a couple things can happen graphically. Let's just think about it graphically for a second. If we have this nice polynomial function, okay, that looks like this. Well, you can see in this function, as you go to positive infinity, our limit just goes actually off into what? Want to take a guess? Negative infinity, right? But it goes off into an infinity, goes off into negative infinity. As we go to negative infinity, what happens to my limit? It goes up into positive infinity. So that's one thing that happens with our end behavior. One thing is it just grows arbitrarily large or arbitrarily small, and then we have infinity. But other things can occur. So what we're going to explore today, besides taking our graphs into infinity as our limits go to infinity, is something like, let's look at that classic function. We've already worked with it. It was f of x equaling, let's do 1 over x squared. Remember the graph of that one? I've done this one a couple times now, I think. Well, maybe twice. So 1 over x squared looked like this, you remember? And then what else did it look like? It was exactly, because it's the x squared one, so it was exactly the same on the other side. Remember, 1 over x went diagonal, kind of? 1 over x squared went like this. So, let's look. Love to do things graphically first, because you get a visual of what's going on when we get into the algebraic part, right? So let's explore the limit as x goes to positive infinity for 1 over x squared. Let's explore it graphically, meaning all we need to do is look at the picture. So when you look at the end behavior of this function, as we go off to positive infinity here, I will clarify this by putting positive infinity, just to make it easier. Doesn't really matter in this case, but where does our graph, what happens to our y values? So again, we noticed on the first one, just went off to everyone agreed. They're just going to keep getting smaller and smaller and smaller, so it goes to negative infinity. So up here, if I were to write whatever that x value is, the limit as x goes to positive infinity of this f of x function, it goes to negative infinity because it goes down. What's happening to this one though? Yeah, does everyone see? It's just getting closer and closer to 0. Okay? It's going to it'll never hit 0, right? And it'll never hit a negative value, correct? You can tell by the function. There's nothing you could plug in for x when you have 1 over x squared that'll make that function either equal 0 or a negative number, correct? So yeah, this function, if you look at the graph, will actually approach 0. So let's think about that. What does that mean when in terms of limits? And you got to, I say this every class, you got to get away from evaluating the function at that point to evaluating where the function is approaching. Remember? That's what limit is. What it's doing as you approach something. So essentially, what we're saying here is, and let's see if it makes sense to us numerically. It's saying, all right, well, if I took and I plugged in infinity, now you're telling me that and let me tell you, I don't need the squared there. Infinity squared, infinity is such a large number. If you square it, it's the same number. Does that make sense? Because number one, what did I say wrong in that statement? Infinity is not even a number, right? So, doesn't matter if you square it or don't square it. 1 over infinity. How does 1 over infinity become 0? So let's think about that numerically, because that's a really important concept. This does not mean 1 divided by infinity equals 0. Please remember that. This means that 1 divided by an x value, as that x value keeps getting larger and larger and larger, becomes 0. Okay? So how does that work? Well, think about it. Well, let's look at it numerically real quick. And we've kind of done this before, but all right, we know we can't plug in 0, so we plug in 1. 1 over 1 is just 1, correct? Plug in 2. We did this, 1 over 4. Right? Dot, dot, dot. Correct? That makes sense now? Yeah, and we talked about this last class. As, because we did this graph in one of the classes one day last week. As your x gets larger and larger and larger, 1 over x squared gets smaller and smaller and smaller and gets closer and closer and closer to 0. Okay? So that's an important concept to remember. In fact, I'm even going to remove the x squared. It doesn't really matter. But the limit in general, as x approaches infinity, of 1 over x okay? That does not mean 1 divided by infinity equals 0, okay? I don't want you to go saying, hey, I found out what 1 divided by infinity is. It's 0. No, but the limit, and again, this is going to be used a lot. This is a really important concept. Doesn't matter if it's x squared, x cubed. It doesn't matter if I change it to 1 over or 5 over x. Do you think it matters if I change it to 100 over x? No, because as long as there's a constant in the numerator, that denominator gets bigger and bigger and bigger and bigger. It's going to approach 0. Not matter. So when I say 1 over x, I mean any version of 1 over x. 1 over x to the 4th. 10 over x squared. The limit as x goes to infinity is equal to 0. Okay? So that's kind of what we're going to be looking at today. What happens? What is this called in a graph? So go back up to the graph picture. When you have this barrier, right? So my graph has a barrier. The x-axis essentially is the barrier. It's never going to go through, right? It's going to get really, really close to it, never going to go through it. What is that? That is an asymptote. But this time, I have a... Yes. Now, when we look at limits at infinity, what we're investigating in this unit, in this chapter, is our horizontal asymptotes. So, when we talk about a horizontal asymptote, so you remember vertical asymptotes. They're vertical lines, right? And they're kind of barriers. Your graph will never cross them. Never cross that imaginary vertical line. Vertical lines have the equation of x equals something. A number, whatever it's going through. What does a horizontal asymptote have an equation of? Yep. All horizontal asymptotes. So in other words, if on a lab, if on a test, I say, hey, write the equation of the horizontal asymptote, it's y equals, in this case, y equals what? What is that y value? It's never going to hit, never going to cross. 0. Yep, so it's y equals 0. Okay? So vertical asymptotes, horizontal asymptotes. We're going to focus on horizontal asymptotes today. Thursday, when we're doing the test review, I'll do a recap of both with some steps and making sure you remember how to find each of them. Okay? So let's go through some examples. And then I'm going to pick up with something you touched upon in your pre-calc class, and we're going to expand it a little bit. Because you touched upon horizontal asymptotes in pre-calc, whether you remember or not, because you graphed rational functions. Fraction over fraction. So we are going to touch upon that. So let's play around. We like to bring in trig and other things, so we're going to do a trig graph. We're going to start with that. We're going to play around with, they're very separate from everything else, so it's good to kind of play around with a trig graph first before we get into all the rules for our polynomials and our rationals. So the one I want you to look at is actually an inverse graph. So we're going to explore the graph of y equals tan inverse x. So what's the graph? All right, to understand the graph of y equals tan inverse x, what should you probably remember first? You probably want to recall. I got to store new colors so it's not always red and green. You probably want to recall y equals tan x. Before we can inverse it, let's remember what y equals tan x looks like. And if you don't remember, you can always pop on Desmos. This is what's great. You can always pop on Desmos to remember what these graphs look like. I think we did kind of I did a refresher of all graphs first class day, maybe. I think I did. So y equals tan x. So tan and sine and cosine, our trig functions are periodic, meaning they repeat themselves every so often, right? Tan has, somebody remember what the period for tan is. Cosine and sine are 2 pi. Every 2 pi, the classic cosine and sine graph repeat itself. Anybody remember what the period for tan is? Pi over 2 comes into play. Double that, pi. Okay, tan repeats itself every pi. All right? So recalling where tan is undefined, where it doesn't work, if you remember your tan graph, it goes from negative pi over 2. You have vertical asymptotes on the original tan graph. And it looks like that. So what's our inverse tan graph? Kind of goes on its... Remember, when you do an inverse, what switches? It's not a reciprocal. It's not 1 over tan x. It's an inverse. Every x value flips with every y value. In fact, if you took every coordinate and flipped the x and y, you'd have the inverse. So your inverse tan graph looks more like this. When you do an inverse, guess what your horizontal asymptote, your vertical asymptotes become, guess what? Horizontal asymptotes. Because we had an asymptote here at negative pi over 2 comma 0. So now I'm going to go to 0, negative pi over 2. So I'm flipping it. And the other one at pi over 2 comma 0 is now 0 pi over 2. And the graph's going to look like this. Okay? So your inverse tan function has nice classic horizontal asymptotes. And if you were to examine the limit as x goes to positive infinity of tan what's that going to equal? Pi over 2. Okay? Because what's going to happen is your graph is going to get really, 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 really close to that pi over 2, because this is now pi over 2, and it's never, ever going to touch it. Now, it is different if you go take x to negative infinity. And often negative infinity, infinity, you have to look at differently because they're the opposite ends of the graph. They're not always doing the same thing. Sometimes they are doing the same thing, like we saw in 1 over x squared. They were both going to 0 no matter which direction you went, right? They were both going to 0. But here's an instance where you see they're not both going to the same value. Because what is the limit as x approaches negative infinity, according to the graph? Negative pi over 2. But y equaling pi over 2 becomes the horizontal asymptote of the tan inverse, and y equaling negative pi over 2 is also a horizontal asymptote for the tan inverse function. Okay? So a couple things are going to happen when you take limits to infinity. All right? You're either going to get infinity as an answer, in which case, if you get infinity, guess what? There are no horizontal asymptotes. All right? So we'll kind of summarize that. In these notes, I kind of like to summarize these in simplest terms. You can then read the PowerPoint for the very detailed. But there's not much detail here on this one. So, if x sorry, not x. All right, so when you're taking the limit as x goes infinity, if your f of x, which is your y value, becomes arbitrarily large, then the limit as x goes to infinity for f of x equals infinity. And if it equals infinity, you have no horizontal asymptote. Okay? So I said three things up here. It's really two different things happen. It either doesn't become arbitrarily large, it gets really close to a value, or it becomes arbitrarily large. But we like to separate 0 out. So another thing that can happen is so we'll say if f of x becomes close, sorry, I can't seem to write today, to a finite number L, we'll just call it some number L. Okay, that L could be 0, it could be 5, it could be pi over 2, that L could be anything. It gets really close to that L, then we say the limit as x approaches infinity, and this can go for negative infinity too, I'm just not writing it twice. As x approaches infinity of f of x equals L. And in this case, the line y equaling whatever that L value is, 0, 5, pi over 2, whatever it is a horizontal asymptote. If it's negative 7, no matter what it is. Okay. So we got to get to, looking at graphs is easy. We just did it. Okay, we were able to see, hey, there's a horizontal asymptote at 0. There's a horizontal asymptote at pi over 2. There's a horizontal asymptote at negative pi over 2. Where the trick comes, as we saw even with vertical, is doing it algebraically. How do we manipulate it algebraically to get this information without graphing our functions? Okay, so that's kind of trick. So let's do, I want to go back to what you have done in pre-calc. In pre-calculus, you graphed, because the horizontal, and I'll tell you right now, basic polynomial, y equals x squared, right? You know it. It's a parabola. Does that have horizontal asymptotes? An x cubed function, any of those basic polynomial functions, horizontal asymptotes? No, we talked about the end behavior of those functions. Remember, if it's an x squared function, they're both going the same direction, positive, they're both going off into infinity. If it's an x squared but it's negative, they're both going down to negative infinity. X cubed is switched. X to the fourth is the same. Any even power, remember we talked about the end behavior, it's both up or both down. They don't have horizontal asymptotes, those functions. Where do we get into horizontal asymptotes? With our trig functions, our natural log functions, or e functions, and rationals. Same way with the vertical asymptotes. We get into horizontal asymptotes when we're dealing with rationals. Do you recall in pre-calc when you were graphing rational functions, how you figured out if something had a horizontal asymptote? Do you memorize? Yeah. That's whether or not something was a function. In pre-calculus, maybe if I start to put it down, it'll refresh. You learned a short trick. Do you remember doing that? Oh, if the exponent's the same, if in the numerator and denominator, if the exponent's bigger, remember that? You literally learned a trick. So what was that trick? Let's just recap it real quick. So basically, suppose f of x is a polynomial function. We'll call it p of x over some q of x. Okay? And again, I'm summarizing. Let's suppose the largest exponent in p of x is m. All right, so in other words, if the function starts 3x cubed, m is 3, right? Everybody get that? And then the largest exponent in q of x is n. So for example, if I had 3x squared plus 2 over 5x to the fourth minus 3. My m is 2, my n is 4. Okay, so I'm just defining. I want to define largest exponent numerator versus largest exponent in the denominator. So first, what happens when m is less than n? Again, my notes will have this in a lot more detail. I like to shorten it for you. What happens when m is less than n? In other words, I have something like 3x squared over 3x cubed or something like that, right? M is less than n. Anybody recall what happened with horizontal? Then we have, well, let's put our cases down. And they're the same. And the third case is we have the larger exponent in the denominator. Does anybody remember from pre-calc what the rule was with horizontal asymptotes with any of these? Anybody? Anybody? No? No? So this was, I was kind of hoping you all remembered from pre-calc because you had to you literally had to memorize this list. We're going to do something so you don't have to memorize the list anymore. All right? But the idea behind it was when m is smaller, y equaling 0 is a horizontal asymptote. But the list comes in handy to check yourself. Okay? If m and n are equal to each other, then you actually have a horizontal asymptote at L where L is equal to coefficient of x to the m over coefficient. You remember that one? Students tend to remember that one. It's kind of like saying, pretend that didn't happen. That's why I have this. So this one's kind of like saying, hey, if I have 3x squared plus 5 over 2x squared minus 7. Remember that? You have, a horizontal asymptote at 3/2. Usually students remember that one because it's quick and easy. Oh, if they're the same, just take the coefficients. There's my horizontal asymptote. And then do you recall, so we have 0, we have L. What do you think happens when the numerator exponents are greater than the denominator exponents. Almost, but just greater in general. There's actually no horizontal asymptote. Okay? Whoops. I keep wanting to put two S's in the word asymptote in the worst way. It does not have two S's. Okay, there's no horizontal asymptotes. Now, and this you do need to recall this. If this is we'll call this one C1. It's like a little sub of C. Okay. If M is exactly 1 more than N, then you still don't have a horizontal asymptote. See that? It's still under no horizontal asymptote. You do have something called a slant asymptote. You do have something called a slant asymptote. Okay? That's where your function, I do have an example in the notes. I'm not going to really spend much time with the slant asymptote today, but it looks like, what's a good picture of a slant? I have one in the notes. It's a nice picture of a slant. Yeah, it's a diagonal. So it might look something like that. And your function might look like that. It'll get close to it. But guess what? The limit when dealing with a slant asymptote, even though it's restricted in how fast it grows, is still infinity. You see that? That's why we recognize them. We know slant asymptotes exist, but does it change the limit? The limit still goes to infinity. There is still no horizontal asymptote when you're dealing with slant asymptote in this case. I mean, there could be a horizontal asymptote somewhere in the problem. And that's nice. If you have that memorized, great. I don't like when you get to calculus, it's just memorize stuff. You want to kind of understand. How can we do this without having to memorize or with checking ourselves or with knowing for sure? We go back to what we've been doing and we do algebra manipulations. All right? We do algebra manipulation. So I want to take you through each of these examples using our algebra manipulation. This is the algebra manipulation I want to see on the lab and I want to see on the test. This is just kind of a quick way to recall, to check yourself. Okay? So the first one I want to do, example 1. So again, we're going to use limits to find out if our rational function has a horizontal asymptote. So I want to take the limit as x goes to infinity. Now, it's always good to do a little recollection of what we did last class. When you look at that function, 3x plus 2 over x squared minus 1, if I asked you about vertical asymptotes, what would you tell me? Because you got to keep in your head vertical asymptotes and horizontal asymptotes, and it's good to do them at the same time so you don't get them confused. We've already learned about vertical asymptotes. We've learned about vertical asymptotes versus holes in a function. What could you tell me about that particular function? Does it have a vertical asymptote? And if it does, where might it be? What do you think? Last class. Wasn't even that long ago. I know it was a very exciting weekend. Yes. Yeah, your vertical asymptote occurs, or a hole. So let's do it general first. It's a vertical asymptote or a hole if you plug in a number that makes the denominator go to 0, right? So right away, we know what will make that denominator go to 0. 1 or -1. How do I know they're vertical asymptotes and not holes? They're not going to cancel. You can factor x squared minus 1 into x plus 1, x minus 1. Will either of those binomials cancel? No. Vertical asymptotes. So without even doing any work, I know if I were to visualize this graph, I got a vertical asymptote at 1, a vertical asymptote at -1, which is great, but I'm not asking about that. I want the limit to infinity, okay? But a little recap. Know when you see your vertical asymptotes. All right. So now, and then keep in mind, and this we will recap on Thursday, with vertical asymptotes, you have to look at what happens as you get really close, remember, to know if it's going, you should have done this on the lab, to know if it's going up to positive infinity or down to negative infinity. Don't forget that. All right, so here's an algebraic trick. Remember what I told you. So let's scroll back for a second. This box, this thing I have in red, that's going to come into play. We're going to use that. Okay? We're going to use that. To do that, what I'm going to do is manipulate this function. Normally, we want to get rid of a lot of little fractions, right? I'm going to put fractions in this. And I'm going to put fractions in it because it's going to help us really easily determine our asymptotes without having to memorize anything. So how do I put fractions in it? Well, here's the trick. You want to divide by x to the n, where n is the largest exponent in the denominator. Let me clarify. When I said divide, I left two really important words out. Every term. Okay, terms are individual pieces of your function. So 3x is a term, 2 is a term, x squared is a term, 1's a term. How do I do that? I do that, and you don't have to show this part, but I like you to know why we're doing things and why we can do things, and it doesn't change the value of our original rational expression. What number can I multiply that by? And it won't change the value of the original expression. There's only one number, everybody. What is it? 1. Everyone agree? I can multiply by 1. What's great about the number 1 is it can look like anything, right? So my 1 is going to look like this. I need the largest exponent in the denominator. What is that? 2, x squared. So I'm going to multiply. Not whatever that was. I'm going to multiply. Everybody see what I did? 1 over x squared and 1 over x squared is the number 1. Great. By distributing 1 over x squared across the numerator and across the denominator, aren't I really dividing everything by x squared? That's all I'm doing. Okay, you don't have to necessarily write this piece. Okay, the next step is important though. So by doing that, I am taking my limit and I'm saying, hey, I want 3x over x squared. I want 2 over x squared. I want x squared over x squared, and I want 1 over x squared. And a lot of this you are going to be able to kind of do in your head once you get the hang of it. This particular one, I'm going to go through every step though. Okay, and it's okay if you skip some steps. But this one, I'm going to take you through every step. It's still a limit. I haven't plugged in infinity yet. It is still a limit. I'm going to simplify. What is 3x over x squared? Well, that's 3 over x, correct? 2 over x squared is just 2 over x squared. X squared over x squared is? And 1 over x squared is 1 over x squared. Now this is where the fun begins. Do you remember what we said? What does this equal? And remember, any version of it, 5 over x, 7 over x cubed, they all go to 0. So now, when I go ahead and plug in my infinity, all right, this becomes 3 over infinity. What does 3 over infinity go to, everybody? Right? What does 2 over x squared go to when I plug in infinity? 0. All right, 1 is 1. 1 stays 1. Everyone agree? What does 1 over x squared go to when I plug in infinity? This is the fun part of math, when things just cancel away and everything works out great. I have now plugged in infinity. I no longer need to write limit. And what is 0 over 1? 0. And didn't we say, we learned in pre-calc in our shortcut, when m is less than n, you get a horizontal asymptote of y equals 0. Now does it make sense? Why is it a horizontal asymptote? Because when you take the limit as x approaches infinity, you get 0. Which means, okay, this means y equaling 0 is a horizontal asymptote. Okay. You can see in doing this, you don't have to write every step, but this is what I need to, like, see this part here? I need to kind of see something like that. I need to see that you did the division and you crossed off what became 0. Okay, so we're going to go through each scenario. We're going to practice a couple of these and go through them. And the algebra can get tricky. That's definitely the case. The algebra can get tricky. So let's do another example. I'm going to do different ones that are in the notes, but that's all right. Oh. So a couple things to remember. When you see x go into infinity, think, ooh, I might have some horizontal asymptotes here. I got to evaluate what it is first, though. All right, so 40, it can be as big as you want it to. It doesn't matter what it is. So let's practice with some shortcuts. I'm not going to write out what we're actually going to divide by. What are we dividing by in this well, all right, I'll write it out because it's our first problem, or only our second problem. I should write it out. Technically, what are we dividing? What are we multiplying by for this one to work? It's 1 over x to the something, right? Yep, we're going to do 1 over x to the 4th, because look at the denominator. What's your highest exponent? 4, 1 over x to the 4th. So yeah, basically what we're doing is dividing everything by 1 over x to the 4th, which means I'm multiplying by 1 over x to the 4th over 1 over x to the 4th. So I'm gonna skip a little bit here. And I'm gonna do this in my head. All right? I'm gonna go through and divide by x to the 4th. Well, in your head, I think you can do 40x to the 4th divided by x to the 4th. What's that gonna come out to? What's 40x to the 4th times 1 over x to the 4th, or divided by x to the 4th? Don't the x to the 4ths cancel? And you're left with? All right, that's what I mean when you can do some shortcuts here. All right, now I have 4. What's x to the 4th, x squared, sorry, divided by x to the 4th? Yeah. Do you see where that one goes to x squared? And then, of course, 1 over x to the 4th. So I'm skipping. You can skip some steps as you get the hang of it. Do the same thing with the denominator. What's 10x to the 4th? Divided by x to the 4th. (8x squared) divided by x to the 4th. Yep. n plus 1 over x to the 4th. So now this is where you get to have the fun and see what goes to 0. Because now you're going to take the limit. And I'm going to visualize putting in infinity for all those values. All right, 40 stays 40. We don't do anything with that. What is 4 over x squared as x goes to infinity, everybody? See the fun part? Right? You get the idea. 10 stays. So I can take away the limit because I just did it. And what am I left with? Yeah, I'm left with 40 over 10, which equals 4. So that is why when you have the same exponents, all you got to do is look at the coefficients. The limit is 4, and that means, what does it mean? That y equaling 4. Quick one, and then I'm going to do one where you're going to say, like, no, it's not that bad. Kept this one nice and short. So this time, and you're going to get the hang of it, and, you know, the goal is you can look at these and know right away what the horizontal asymptotes are, what the limits are, and stuff like that. But let's go through the process. What am I dividing each term by for this problem? X, right? 1 over x. It's 1 over x over 1 over x. I'm basically dividing each term by x. Agree? Because it's going to be, we're going to use this. Okay? So when I divide every term by x, I get limit approaches infinity of, that's going to give me x to the 4th, right? Over what? What's 2x divided by x? 2. Okay. So this one's a little different. What is the only one that actually goes to 0 when I plug in my infinity, everybody? Yeah, 3 over x. Don't take x to the 4th. That's not going to 0. You see that? That's not a fraction. Only something over with an x in the denominator. So that goes to 0. So what am I left with? I'm left with infinity, right? Because I'm plugging in. It's technically infinity to the 4th. But what's infinity to the 4th? We'll take infinity to the 4th power. It's all the same. Plus 0 over 2. All right, think about this. You have infinity, you add nothing to it. What are you left with? Infinity. You take infinity and you divide it by 2. What do you still have, everybody? Yeah. What's my answer? And when I get a limit of infinity, guess what I have? No horizontal asymptotes. Do you want here's the tricky one. It's not as bad as it's going to look. Okay, same idea applies, but you got to kind of think a little bit critically on this one. Example 4. sorry. That is a 4. Yes, I'll try to make that look more like a 4. There you go. What makes it tricky? The square root. So let's talk about the square root for a second without actually doing the square root. All right. Remember, we got to divide by the highest denominator, exponent in the denominator, correct? When you look at that, what appears to be the highest exponent in the denominator? Appears to be x to the 6. But let's talk about that for a minute. What is the square root of x to the 6, everybody? Please tell me you know this. It's the square root of x to the 6. Yes. Square root, you just cut exponents in half. And x to the 6 inside a square root is really an x to the 3rd outside a square root. Okay? The other way I want you to remember this, because sometimes you're radical. So I'm giving you one where the radical's in the denominator. I think on the lab I give you one where the radical's in the numerator. So the denominator's fine. So sometimes you got to think about pulling that x value out of the radical, but sometimes you got to think about putting it back in. So let's suppose I had, this isn't this problem, this is just the side. So I choose a different color. Let's suppose I had an x to the 10th. All right. And I know I need to divide that by x to the 5th. Or I'll come up with something. Suppose I want to divide by an x cubed outside the radical. Do you see that? I want to take an x to the 10th inside a radical, but divide by an x to the cube outside a radical. In other words, if I were to pull this x to the cubed and bring it inside the radical, what is it inside the radical? Yes, it's x to the 6. You have to think about whether you're putting things in the radical or out of the radical. Does that make sense? So you got to be really careful when doing this one. All right? So now, that's not an x to the 6, right? Because it's inside a radical. It's really an x cubed. So what's my highest exponent? X cubed. I got to divide everything by x cubed. Yes. This one does. Yeah, because that was the example I gave you. Sorry about that. That's a 10. There you go. That's 10. So when doing this problem, I'm just going to go right to the dividing. I am essentially doing 1 over x cubed, 1 over x cubed. You just got to be careful of what it is when you put it under a radical. So let's do it. All right, so what's 10x cubed become when you divide by x cubed? We're fine. It's just, all right, you're getting the hang of it. 3x squared over x cubed is, okay, so we're good with the numerator. When you do the denominator, the whole, and you got to be careful because sometimes parts and numerators are under radicals and parts aren't. So make sure you're doing the right thing. This entire denominator is under a radical. So when I bring it inside the radical, it's actually 25x to the 6 divided by what? X to the 6. When I bring this, right, into the radical, does everybody see that? It becomes 1 over x to the 6 under the radical. All right, so just be careful of that. And like I said, there's one on the lab for you to practice. But do be careful of that. It's just more of that algebra manipulation to get what you want. All right, so let's do, what does this first term become? Remember, we're dividing by x to the 6, so it's 3 over, right? Right? Oh, wait, it's not it. Oh, so I ignore what I just did. Just pretend that never happened. I know it's recorded, so we can never pretend it never happened. What is x to the 4th divided by x to the 6th? Yep. And this is 2 over x to the 6th. So be careful. It doesn't really change much of what we're doing. So don't worry about that, because it's really not going to change much of what we're doing. We're still going to go through it and wipe out and see what goes to 0. So, oh, that goes to 0, right? Even under the radical, it goes to 0. Whoa. Hit the sport the news or something. Be careful what you got left, though. Now I'm going to evaluate the limit. I don't need to write limit anymore. I plugged in my infinities. I'm left with 10. Right? And my answer of 2. So just you got to be careful when you are working with those particular limits. This will have horizontal asymptote at y equals 2. Definitely a horizontal asymptote at y equals 2. Now, I want to do a little adjustment here and show you something. We took it to positive infinity. Okay. What would happen if we were to approach this as x equals negative infinity? So let's think about that a minute. Right? I took it to positive, and that's great. Because remember, so far, we only know what's happening the right side end behavior, right? This function's going to get really, really, really close to 2, but never touch it. All right? So here's a little trick. If you're asked to take it, because hopefully you've all been thinking this the whole time, right? What do I do if I'm going to negative infinity? Haven't you all been thinking that? No, you don't care. Maybe some of you are sitting here like, I was actually thinking that. Okay, here's the trick. You can now divide numerator and denominator simply by the negative x cubed. That's how you can get around that. You can divide, in other words, when I do this part, of course I picked a really long problem, but that's all right. So watch. Same problem. Let me move it up. Oh, I need it down for a second so I can see what it is. You see what I did there? Is it still a 1? Yeah. Why am I using negatives? Because I'm taking it to negative infinity. It may not equal 2 anymore. Not a lot changes. In fact, let's kind of look at, I'll try to leave, this is what we did. I still have the other one up top, all right? So this is, I'll draw a line. Here's doing negative. So let's kind of think about what changes when I do this. Well, my 10x cubed is now being divided by negative x cubed. So what changes? 10 becomes, my positive 10 becomes, yeah, it becomes a negative 10. My minus 3x squared actually becomes positive. Why did I have 3? Oh, yeah, my minus 3 over x becomes positive 3 over x, right? My plus 8 over x cubed actually becomes, yeah, here's the funny thing. And this is why it matters with radicals. Because if you do this and there wasn't a radical, we would negate the bottom, but the two negations would cancel each other out and we'd still get positive. You see that? We'd still get the same answer. The radical changes that. Because when I put it inside, I'm squaring it. What happens when you square that negative? It automatically becomes, you can't put the negative under the radical. Do you see that? Because essentially what we did in this first problem is we took, it was up here more, that 1 over x cubed, and we squared it to get it inside the radical, right? And it became 1 over x to the 6th. What happens when you square negative 1 over x cubed? Doesn't it become positive? So do you see the radical does not change at all because it had to become positive when you square it to put it inside the radical. So the radical actually becomes the exact same values because this gets squared. So negative 1 over x cubed squared equals positive. You're still dividing by x to the 6th inside the radical. So, yep, I still get 25 minus the 1 over x squared plus 2 over x to the 6th. So the only thing that changed was that number, that 10. I still, 0, 0, 0, 0, and now I have negative 10 over radical 25, which ends up equaling negative 2. Radicals are funny like that. You can't visualize, you probably can't visualize this graph, and to get that into Desmos would take us quite a few moments. But you can, that's something when you're going through your notes studying this weekend, because that's all you're doing is studying for calculus all weekend, right? When you're going through those notes studying, play around with these functions, put them in Desmos so you can visualize what we got algebraically. It helps. This particular graph is kind of funky looking. What we know about it right now is we definitely have, somewhere over there it's touching that one, right? And then it's touching at negative 2. It actually kind of goes, and this is a cool one to look at. It kind of goes something like this. All right. Couple words about asymptotes. We'll revisit this in chapter 4 when we really get into graphing these functions. Vertical asymptotes are hard walls. You never go through them. Ever. Ever. Horizontal asymptotes are soft in the middle and become hard walls on the ends. You can bypass a graph, can bypass a horizontal asymptote as long as it doesn't as it goes off into infinity. Does that make sense? I know, it's funny. Vertical walls are always solid. Horizontals are a little soft in the middle. We can go through them. But horizontal asymptotes, as you approach infinity, become solid walls where you can't touch them. Okay. A little bit about our logarithmic functions. All right. Because horizontal asymptotes and taking limits at infinity is kind of all about what's happening at the end behavior of functions. So it is a good idea to kind of go through some simple limits when talking about the end behavior. I want to make sure you have this in your notes of some functions like e to the x, e to the negative x, and ln x. Okay, so we want to talk about those for a minute. It's really important you kind of get these functions down So play around with them, plug them into Desmos, make sure you know what they look like. All right, we've already graphed them. We're not graphing them right now, but let's talk about the limits. So if you don't remember what e to the x looks like, all right, we'll recap. Okay, if I said right now, everybody draw an e to the x function without using a graphing calculator, could you do it? Right. So here's what you want to go. Quickest way to do this, because you know if you don't have, you're not gonna have the graphing calculator on test, and you gotta be like, oh my god, what does the e to the x function looks like? Start with 0. What's any value to the 0 power? All right, it definitely goes through that point. Now think about it. E is just a number, 2.7. Right? So when x is 1, what's e to the 1? When x is 2, I want 2.7 squared. What's going to happen? It's just going to keep getting bigger and bigger and bigger, correct? There, we'll do that. Looks a little better. Now, what happens on the opposite side? E to the negative 1. What's e to the negative 1? Oh, it's going to be 1 over e, right? 1 over 2. But that's going to keep getting smaller and smaller and smaller. There's your e to the x function. How does that function change if I made it e to the negative x? Tell you what point doesn't change. Yeah. Guess what happens when x is 0? It's still 1. But now, what's going to happen to the graph? What do you think? It's just going to go the other way, right? So in this time, it's going to start up here and go that way. Okay? So get those graphs down. It will be helpful. The other thing is your LNs. Don't forget your LN graph. This one, instead of 0, 1, right? It's 1, 0. Okay, it's the inverse of that first graph. So this one goes like this. It's just the inverse. That's ln of x. And then okay, that should be all you need. So let's talk about limits of each of these as they go to infinity. First one, the limit. These are important limits to know. The limit as x goes to infinity of e to the x. If it wasn't my kid, I wouldn't answer it. I'm so sorry. I'm in classes. Quick. Seriously? Today's the 31st, yes. Okay. I'll talk to you later. Bye. Apparently, if you ever want to take a professor who cancels a lot of class, take Lance Hemlow. Anybody have Lance? I love Professor Hemlow. He literally called me to confirm that Professor Hemlow canceled class today. I am so sorry. Anyway, let's get back to our graphs. Isn't that nice? And you just call mom to make sure class actually did get canceled because he didn't believe the professor. So when you see infinity and there's no negative sign, you're assuming positive infinity. So what is the limit as x approaches infinity of e to the x? First graph. In other words, as x is getting bigger, what's happening in my graph? It's not restricted. It's just infinity. Good one to remember. How about the limit as x approaches negative infinity of e to the x? Everybody, look at the graph. What is it? You can show me with your, you can like, 0, right? That's going this way. What's happening? It's 0. Okay. Next one, limit as x approaches infinity of e to the negative x. So are you going to have to know these? Yes, because you have to be able to reconstruct. And if you can reconstruct the graph real quick and draw yourself a little sketch, you can get any of these limits. What's the limit as x approaches infinity to the negative x, everybody? 0. It's this graph over here. See? What is the limit as x approaches negative infinity of e to the negative x? Yeah, it's just infinity. Okay? ln. ln's a tricky little thing because we can only approach 0 from which direction? Yeah, technically you can only approach 0 from the... Yeah, so I'm going to put that on the limit. I'm only approaching 0 from the right. We're not going to approach infinity in that case of ln of x. And what's it equal? What's the limit as x approaches 0 from the right of ln of x? Negative infinity. So this is where it's important to put the negative sign, right? That is actually negative infinity. And the limit, last one for here, as x approaches infinity. Yeah, it's infinity. One last one. I'm going to make you debate this one. You ready? I'm not going to draw. I should be able to see a lot of perplexed looks. Yeah? So it's not an inverse function. We don't have domain restrictions. We're going to do it without domain restrictions. We do have domain restrictions when we do sign inverse. Okay? No, I'm not doing a domain restriction. This is a domain restriction. So picture it. What you can picture it, right? What's happening to the graph? It's doing what? Oscillating. It's called oscillating. And it's oscillating between which two values? -1 and 1. Okay. So that's a case where it does not exist. Wasn't a trick question. But think about it. And this is where when you're... So here's the thing. Polynomials, always nice and easy to work with. You just plug your numbers in. They work out. They're infinity, whatever it is, it's fine. Rationals, got to do a little algebra manipulation with those. The transcendental functions, which are your trig functions and your e's and your ln's. What do you have to know to really work with those functions? What do you got to be able to picture every time you're working with one of them? The graph. You got to picture the graph. It's kind of, that's the only way. Cosine would be the exact same case in this one. It wouldn't exist. All right. So you got to work with, you got to know those graphs. So this is kind of my plug to be able to visualize any of those graphs. Okay.